Hi, and welcome to this talk on developing and testing REST in a cloud IDE and running it on a microcontroller. My name is Ulf, and I'll be presenting together with my colleague Jens. We work for Red Hat on improving the connectivity options for embedded devices and building an open source IoT connectivity and device management service in REST. You can find us and our work on GitHub and Twitter. Today, we're going to talk about how you can use an online IDE like Eclipse Che to build applications that can run both in your browser and on embedded devices. But let's start with some background on the work we're doing with the Drogue IoT project first. Drogue IoT is an ecosystem built around providing the tools for developing microcontroller firmware with various connectivity options on the device side and endpoints in the cloud for devices to send and receive data to or from. Today, we'll primarily focus on developing the device-side software in the cloud. Let's start by introducing the Rust embedded side of things first. Embedded systems are still largely written in C and C++. When the Rust project started, it wasn't immediately clear that it would be such a good fit for embedded, but as the project matured and the core capabilities of the language was stabilized, several experienced embedded developers started to work on building the ecosystem around it. And Rust is a great fit for embedded primarily because of these three parts. First, Rust allows you to write safe code where a lot of common programming mistakes simply cannot be made. So access to mutable state is checked at compile time, which means that data races is actually not possible in safe Rust. There are times when you have to write unsafe code, and it can be done, but you are able to limit that part to a small area of your code. The Rust compiler produces fast code, and in some cases better code than a C compiler because its type system allows the compiler to potentially infer more optimizations than a C compiler would. But the best part from my point of view is the tooling. Rust have a build tool and dependency manager named Cargo that is used by most projects, embedded or not. And open source libraries are usually published to a central repository, allowing you to easily mix and match libraries for your application. Some libraries work with the core language, which means that you can also use it in your firmware. In the embedded C world, there's a lot of work going into the real-time operating systems. In Rust, there are also a few such operating systems available, but in my experience, the need of an real-time operating system in Rust is less because there's a lot of great tooling that allows you to pull in only the modules you want. There's no need to sort of centralize all the modules in a single project. So instead, you have several runtimes in Rust that help with some of the core RTOS functionality like task scheduling. Rust also has support for writing asynchronous code in a synchronous way called async await. This allows for writing very power-efficient code where a task can automatically yield execution when waiting for I/O, and the executor can then put the microcontroller to sleep until it's woken up by an external event, such as an interrupt. One such project for async Rust is Embassy, and it's a project within the community driving the development for an async runtime for embedded devices, as well as peripheral access in an async fashion. So when you talk about an async task, it's essentially what people call future or a promise in Java. And in Rust, a future can be polled, and there will be an attempt at making progress whenever it's being polled. So if no progress can be made, then the API allows the future to register itself with a waker, which is a runtime-specific construct that allows keeping track of tasks, such as the tasks run status, and then another piece of the code can then wake that task when it's ready to run. So, but from the application code perspective, a future is awaited, and Rust provides the syntactic sugar to write these futures and using them. An important note with futures is that they cannot be preempted, and they yield execution by returning the pending state when they are polled. At Drogue IoT, we're maintaining an actor-based framework for writing embedded firmware. And the actor model is basically centralized around an actor, which maintains its own state and modifies that state in its processing logic or based on messages sent to it from other actors. So we believe that actor model is a good fit for embedded systems because it naturally handles the concurrency that arises from interrupts and multiple tasks. And paired with this Embassy async runtime, you get a very efficient and low resource usage in your firmware with pretty good hardware support as well. So that was a quick intro to Rust and the Rust on embedded. One interesting aspect of Rust is that web and embedded development actually share a lot of similarities. So we're not going to look at those similarities and try to understand how we can write software that reuses a lot of code for both of these platforms. First, let's compare a runtime such as Embassy with WASM. WASM is short for WebAssembly and is, as the name suggests, an assembly language for the web. What this means in practice is that you can write code and compile it and run it in your browser in different programming languages. And Rust is one of the languages other than JavaScript that is getting improved support for web browsers day by day. And you can easily invoke JavaScript code from Rust and vice versa. And similar to Embassy, the browser runtime is an event loop that uses futures and promises to capture these units of computation that is performed when the runtime chooses to. And in fact, you can actually run their Embassy runtime within your browser. So it's a very good fit. On top of the runtime, you have the frameworks. And in the JavaScript land, React is a well-known framework that allows you to compose applications using components, and the components manage their own state and react to events. And in a very similar way, the actor model in Drogue Device have actors that maintain their own state and react to messages from the outside. So you can see these are very similar ideas. So what if, we can see there are a lot of similarities here. So what if we could reuse our code across embedded and web applications? For this to work, the tool set to develop these applications must be available on the developer machine, which tends to become complex when the target platforms differ. So what if we could also develop this application in the cloud? Imagine being able to build and test your application logic in your browser, and then build a firmware for that same application for your embedded devices. Is this a good idea? Maybe not, but it's fun, and it's an interesting experiment. So let's say you have a simple web app with a button element and a text field that changes state based on pressing that button. And the embedded version of that would be like a physical button and perhaps a LED reacting to pushing that button. Conceptually, these applications have a lot of the same business logic, but the I/O peripherals they use are different. At the surface, this kind of looks easy, but there are a few things that make it more complicated. First of all, an embedded toolchain is more difficult to get right. But using a cloud-based IDE, then the toolchain can be prepared beforehand. And moreover, the setup code for embedded and web applications are different, so they need to be separated. However, the application logic can be separated from the setup code and tested independently of the microcontrollers. But still, for experienced users with the microcontroller, you can always rely on the traditional step if you want to. So now over to my colleague Jens, who will show you a demo of an application running both on embedded devices and in the browser.
Okay, so here is what we have as a device. That's what we start with. That's a microbit, which has an LED. First step is we have a classic project on our local machine. We compile that, we flash that, and run that on the device. So that's a pretty standard thing. We have an LED, and when we press a button, the LED toggles between another LED. So we can see there's a log, there's something happening. We have everything, the source code in a GitHub repository. This is also for you publicly available. And now we will go ahead and get that into our Che instance. There's a fresh instance of Che. You have to set that up. You can log in. And the first step that you need to do then is to create a new workspace. And here you just paste the URL of the Git repository. So what that is doing, that is firing up a lot of components on the cluster side. So that will take a little bit. It needs to download all different kinds of container images, spin up processes. So if you're unsure if this is going or if there's something waiting, you can take a look at the logs. So you should see a little bit of progress. But in the end, it takes a few minutes maybe, and then the project is up. So now the workspace is firing up. Again, for the first time, it needs to set up a few things, import the source code. So again, a little bit of patience is required. The next time you open that workspace, that is all much faster because it has been initialized and persisted on the cluster. So there you see a little bit of progress. It asks you if you trust the project. Yes, of course you do. What could go wrong? It notifies you, hey, import is going on, is finished, and then it opens the README file, which we can close now because we will just dive into the source code. The first thing of notice is the dev file. That is basically the description of the project we just imported. That contains the location of the source code. That contains also which container images we are running as part of the IDE. So there's a specialized Rust container that we have with our stuff in there that we need. And there's a list of commands that are pre-prepared so that we can run them easily later on. We also have the toolchain definition. So these are the target devices that we want to have. And the compiler version 2. So we're using a nightly compiler because we need a few features of that. This is the main entry point for the source code. We will come back later to that, but you can see this is Rust code and the IDE opened that perfectly. On the side, we have a few options here, a little bit of tooling. We have the Rust dev container that we just saw before, which is a Docker container. We got the tasks, and what we can do now is just open a terminal, and that is a terminal inside of the container with the Rust tooling. Now you can see we can run cargo, which is the development tool that you need to compile and fetch dependencies. And the first thing it does is it downloads the tool chains that we just saw as a definition before. Again, that takes a little bit. It is cached then in the local state of the cluster, but there you go. You got the cargo. And then the second time you run that, it's much faster, of course. So what we do as a first step is we just run the check command. What that does is it again fetches dependencies. It also does not a full compilation of the code, but it does like an intermediate file compilation. It checks if the syntax is valid, if everything checks out. And again, that might take depending on your internet connection and on the number of dependencies that you have, that might take a bit. So here we will just wait a bit and skip forward because this is not interesting to see for you. So here we go. It's still downloading a few extras. By the way, this is pulling partly from Crates.io, which is the central repository, and from GitHub. So that's perfectly fine to have that in a local Git repository if you want to do that. So you see it's building, checking, but it's not doing a full compilation. It's only checking to verify everything is okay. And everything's fine. So the next thing that we can do is we can actually compile that. So we're using the task from the sidebar to do the emulator build. Again, it is now compiling and is compiling to the WASM target. So you see it is much faster now because all the dependencies have been pulled in and the source code checked out before. So it only needs to compile now. And with that, we can take a look on the left side. There is the index file. So this is the file, the HTML file that gives us the web UI, which emulates a little bit the device. We have LEDs and the input checkbox. If we refresh, we see a package folder now, and that contains the WASM binary. So that's basically the firmware compiled to binary. Now, when we load the index file, and we can do that by running the emulator that spins up a Python web server serving local static files, the index file that we just saw. Che detects that and asks us if we want to open that, and we can open that in the preview. So basically what happens here is it loads the file from the cluster into your local browser, and the whole logic is running in your local browser now. And you can see when you toggle the LED, then the LEDs flip. So it's a rising edge trigger. So you have to click twice. Only when it's going from false to true, the LED will toggle. Now let's take a look at the source code. As mentioned before, you have to set this up for WASM and for the actual device. So this is a section for WASM. This is the section for the microbit. Wiring up of the hardware or the components from the index HTML file is a little bit different. But when you initialize the device, that is exactly the same code for initializing and all the same code later on too. So let's take a look at the device itself. That consists of the actors. It defines how this is mounted. And then we can look at the actual source code where the logic is. So this is the application actor. For one, we can see the button event is mapped to a toggle event. So whenever you press the button, it will issue a toggle command. We have the event loop for this actor, evaluating the toggle command and then performing something to toggle, which basically flips the internal state, negates that. And once it did that, it will review the state, update that, and that toggles the LEDs. As you can see, one LED is inverted, so it's always one active, one odd. And now we're just going ahead and change that. And this is like a very basic example of changing application logic and now simulating that change and trying to figure out if that works as we expect that. So we rebuild, we reload, and now you can see both LEDs toggle in sync because this is what we just changed. Now, the next step would be to actually try this out on our actual device, the one we saw before. So first of all, we do a check again, everything checks out. And then we do the firmware build. So that is now, you see, recompiling because it's now not compiling for WASM, but for the actual target of the microbit. And everything is happening inside the cluster. All the toolchain is there. And what we have now is we have the binary on the cluster. Now, in the next step, I will switch camera and will actually take that, download that from the browser, and flash that on the device, which is attached to my local machine. So there we go. Firmware build. Then you can navigate on the browser to find the binary, and this is now not the WASM but the actual binary for the microbit. We download that to the local machine. Now I have to open the terminal window, take what we had before, and swap out the file. This is now the file from the download. And now you see old state, it's flashing. And now we got the change logic on the actual device. So we have the full circle. And now back to the slides. So the conclusion we saw in the demo, it was a quick setup. Yes, it takes a while to download, but the actual setup was rather quick because we just copy and pasted a prepared link from the Git repository. So there's not much you have to do, it's all automated. Still, we had the full tool chain for the device. We can quickly test the device logic code in our web browser. So if, for example, someone would not have access to a device, still you could test that out. And we can all leverage the tooling provided by Che for doing that. So does it really solve all the problems? No, probably not. But it solves some of the problems. Is it ready for production? Well, this was a demo. This was a proof of concept. This was fun to play with. But it is a very powerful tool that you can leverage, and you can customize this completely to your own needs. So what we showed you is a demo, is a POC, but you can actually leverage that to build your own thing ready for production. And you can try this out yourself. All the code is open, so you can just go ahead and test it. What could be next is, well, better language support for Rust in Che. There's still a little bit of feature gaps, I think. What could also be interesting is web USB support. So we downloaded the firmware on the local machine and then flashed that manually. But it would be possible to actually leverage web USB support in the browser to directly flash from the browser to a device. Not all browsers support that, so might be tricky. Maybe web USB support is also going away, but it might be interesting to check that out in the future. And that concludes the talk. Thank you very much. So thank you for watching. We have a few questions that need answering. So I will read out the question. First question is, does Rust by itself have any possibilities for tasks, synchronization, asynchronous invocation compared to C and without any third-party libraries or RTOS? So there was an answer in the chat already, which I think is partly the answer, but I leave that to Ulf to answer because this is also important on the embedded side, which is a little bit different.
Yeah. So as you mentioned, that you can use, if you have the standard library available, then you have threads and all of that. But on these tiny embedded devices, the standard library is not available. So things like mutexes, tasks, async invocation, and so on needs to be provided by third-party libraries. And as you saw in the slides and also in the example firmware, we're using an async runtime, which allows running asynchronous code. And the difference with it and using the standard library is that this is much more lightweight. It doesn't require to have a heap allocator to use it. And yeah, there's also other runtimes that are more, let's say, similar to what you'd see in a typical RTOS. Like one is named RTIC, RTIC, and in general, as what's mentioned there, is that you have this cargo crates.io, which hosts tons of libraries And the Rust toolchain just makes it really easy to sort of compose your application from these libraries rather than needing to have an RTOS which has all of it included. So you get a lot of stuff for free since Rust has such a built-in experience for downloading third-party libraries.
Yeah. So another question regarding, I think, the embedded side for Ulf. So why use Embassy for embedded? Is it more suited than Tokyo for this kind of hardware?
Yeah, so that touches briefly on what I just said as well, because Tokyo requires the standard library to be available, whereas Embassy doesn't. And that's mainly one of the reasons to use Embassy. The other one is that Embassy provides drivers and hardware abstractions for a lot of these peripherals that you get on the microcontrollers. So things like SPI, random number generators, tons of other stuff you get supported in Embassy as well. So it's more than just a runtime.
And another question might be, what is the state of embedded Rust?
Yeah, I can give a go at that as well. There are several companies using it. I think I know of 7 companies actually using embedded Rust. But the ecosystem is, of course, will not necessarily be as updated as the existing ones. But I think there's been a lot of development on it, and lots of passionate Rust and embedded developers working to improve it. So it's a very vibrant community.
So if you're interested, where can I learn more? That is also one question.
Yeah, so there's this link for the firmware that I think you will get, and then also there's if you Google Rust embedded, then you will probably end up on one of these GitHub repositories for Rust, and it has a lot of these very introductory tutorials. If you have, let's say, you have a microbit and you want to use it, there's actually a book called the Discovery Book that covers everything from getting the tool chain up and running and playing around with the device. So if you go to that Rust embedded working group repository, there's a lot of links there to others. I can also provide a link here in the chat.
Okay, I think that is it. Thank you for watching.